I'm Mark Kavanaugh for Cavi Coaches, and today I'm going to coach you up on a lab to prove the law of conservation of energy. Alright, so the setup we have here today is I have a lab cart. The lab cart has a spring-loaded plunger, and that plunger is compressed against the spring, and on the ramp I have an attachment that remains stationary so that that spring, when deployed, can push the car and cause the car to move. So what I want you to do is, for the setup that I have here, let's go ahead and pause the video and draw an energy bar chart for that situation.
All right, so what we're going to do is we're going to draw an energy bar chart. So the first thing we have to do is define the system. So in the system, we have the spring, the car, and the earth. And of those things in the system, what has energy to begin with? We know that the spring has energy, so that's going to be stored spring energy. So we draw a bar and label it stored spring energy. And then we know that the energy is transferred from the spring to the car. So for this situation, we have all of that stored spring energy changing into kinetic energy of the car. So now we're going to write our conservation equation. Stored spring energy plus work is equal to kinetic energy. And in this case, since all of our arrows stay inside the system, all the energy flows inside, the work value is 0. So stored spring energy is equal to kinetic energy for this situation.
All right, so one suggestion that my students made is that we could change the incline of the ramp. So what does that do is that's going to effectively change our energy bar chart. So what we're going to do is we're going to look at the situation where the car has the spring compressed at the bottom of the ramp, which we'll define as 0, and the car reaches the highest point, which is going to be our final situation. So go ahead and pause the video and we'll discuss drawing an energy bar chart for that situation and looking at the conservation equation.
All right, so drawing a bar chart for this situation, we're going to define the same system, the spring, the car, and the earth. And again, what has energy to begin with? Well, the spring. The spring's what has energy, so we have stored spring energy. Now the energy flows from the spring to the car, and the car transfers energy to the earth in order for it to have gravitational energy. So we know in this situation that the final situation is when the car reaches its highest point, and it is all gravitational potential energy. So now we write our conservation equation. Stored spring energy plus work is equal to the gravitational energy. And again, all of our arrows stay inside the system, so that means all the energy is conserved. So that means there is no work. So that means for this situation, we have stored spring energy equaling gravitational energy.
All right, so now we saw both conservation equations, and we can see that stored spring energy is going to equal kinetic energy in this particular situation where we've got the ramp horizontal. So what we are going to do is we're going to discuss things that we can measure and change about this situation. So go ahead and pause the video, write down your observations, and then I'll show you a list of what my students have said in the past. All right, so some of the things that you saw my students say, and hopefully there's some of the same things that you said, is that we could change the mass of the car. So I have bar masses here that we can continually add to the car, and that would change the mass of the car. Another change that my students said that they could make is we could lock the spring in different positions and not compress it as much, which is true. We can do that. The problem is we don't have enough positions to lock it in to get enough data to make this as accurate as we could. So what we're going to do is we're going to leave the compression of the spring a control, so our stored spring energy is going to be a control. And the thing that we could measure for the horizontal situation is once the spring is deployed, we can measure how fast the car is moving as it moves across the ramp. How are we going to do that? Well, we know it's moving at a constant speed, and we have markings on the ramp, and we can time it from one marking to another, so that way we can see how fast it's going. Since the speed's constant, we can just take its change in position divided by the time you get on your stopwatch, and that'll give you the speed of the car. Now, for the situation where we have an inclined ramp, so that's where we're taking stored spring energy and changing it into gravitational energy. So let's go ahead and pause the video at this point and write some observations and measurements that you can make for this signal. All right, so you got to see a list of the changes that my students would have made. Hopefully there were some of the same that you said. So what we said they could change is the mass. And actually for this particular situation, it makes it much simpler for us to figure things out in terms of meanings of slopes and things when we make a graph. If we change the weight, what's the difference between weight and mass? Well, remember, weight is the mass that we have of the car times the gravitational constant or acceleration due to gravity, which is 9.8 meters per second squared, or 9.8 newtons per kilogram. We can change weight, which is mg, so we're going to have to calculate that. And we can measure the maximum height in which the car reaches. And it's going to take a little bit of math for us to do that. So we're going to go to the whiteboard and we're going to figure out how are we going to measure the change in height.
All right, so we have an inclined ramp, and we're trying to figure out the maximum height to which the car travels. So if we sketch the starting position of the car, we know that the car is going to reach a maximum height at some point. And what we need to know in order to find that maximum height is we need to know the angle of incline. This way we can find the maximum height at this point. Now we also need to measure the distance that it travels up the ramp. So this length here we'll call L. And we have a right triangle now where H is the opposite side and L is the hypotenuse. So we're going to use some trigonometry. So we know that opposite over hypotenuse is sine. So we can use L sine theta, hypotenuse times sine theta, is going to equal the opposite side. So L sine theta is equal to H. And we're going to use this equation to find the change in height of our car.
All right, so you can see the change in height is going to be a little complicated. So remember that you're going to find how far it traveled from the time the spring was deployed until it reaches its highest point. And then you're going to take that and you're going to multiply it, that length times sine of the angle. And you can see that the angle is this value right here. All right, so at this point, you know which lab you're going to be doing. This lab, we are going to conduct the horizontal ramp where we're going to change the mass and measure the velocity by timing different positions. When you're done, you're going to create this graph right here where you're going to graph velocity on the vertical and mass on the horizontal. Now this is a little complicated to linearize to make a straight line graph because you're going to have to do a couple things to each of the variables, one to the velocity and one to the mass. Not all both at the same time. You're going to make one change based on what you see, and then you're going to see a second thing that has to happen to the opposite variable using your graphical method summary sheet. So let's go ahead and collect data for those labs, and we'll come back and we'll wrap it up. As soon as you're finished collecting the data, make sure you create a graph, straight line graph, find that mathematical model, and we'll wrap up all of everything and what it means when you're done with your graphs.
So we're going to wrap this lab up, and we can see we're graphing velocity versus mass. And when we graph velocity versus mass, we get a sort of inverse relationship. And we know it's a sort of inverse relationship because I gave you the hint that you're going to have to use two methods to make this a straight line graph. So we're going to start first by plotting what our graphical method summary sheet says. This looks like an inverse relationship. So we're going to graph velocity versus inverse mass. When we graph velocity versus inverse mass, we get this non-straight line graph, which means we're going to have to go through this process again. And this time we're going to have to do something about velocity, which is going to be squaring it in order to make this a straight line graph. So we square the velocity, we square the units, and we're still graphing 1 over mass. So now we're going to create our graph of height versus weight, and we can see that it's an inverse relationship. And this one is a true inverse relationship. So we graph height versus 1 over weight, which then means we have to change the units from newtons to 1 over newtons. And this, for each of these graphs, is going to produce a straight line graph. So now we need to go to our graphical method summary sheet, and this is going to be a combination of two. Y squared is equal to m1 over x plus b. And for our height versus inverse weight is going to be y is equal to m1 over x plus b. So now we're going to substitute in the symbols that we have, each of the variables. So this is going to be v squared is equal to, and you should have found a slope value for velocity versus mass to be somewhere around 0.26. And the unit's going to be kind of messy. When we work the units out, it's going to end up being kilograms times meter squared over second squared. And that's going to be multiplied by 1 over mass. So we'll come back to the units on the slope and the value of the slope in a second. This graph, we have y, which is h, is equal to, and this slope should be about 0.13. And the unit on 0.13 is going to be meters divided by 1 over newtons, or we multiply by the reciprocal and get newtons times meters, and that's going to be multiplied by 1 over weight, or 1 over mg. And for both of these, the y-intercept is going to be 0. Now, what does the slope value mean? So notice that this slope is twice as big as this slope. So to figure out the meaning of the slopes, let's simplify these units. So a kilogram meter squared over second squared. Well, I know a kilogram meter over second squared is a newton, so they should have the same units. And a newton meter is defined as a joule. So a unit on our slope is joule for both straight line graphs. Now our controlled value in this lab was the stored spring energy, which our unit of our slope is energy. So our stored spring energy, when we had the spring compressed and we applied a force to it to figure out how much force, we calculate the amount of energy, and the energy was about 0.13 joules. And we can see that that matches up very well with the slope that we got for the height versus weight graph. So that means the height versus weight graph is h is equal to the stored spring energy divided by mg. And for the velocity versus mass, it's going to be v squared is equal to twice the stored spring energy divided by the mass. So what does all this mean? So let's look at the equations individually. Well, we know that if we solve these equations for each of the energies, we're going to get that us is equal to 1/2 mv squared. us is equal to mgh. Well, if we remember from our bar charts that we created at the beginning, we know that the stored spring energy for this one was equal to the kinetic energy. We can replace stored spring energy with kinetic energy, and that means kinetic energy is equal to 1/2 mv squared. In this particular lab, we know that our stored spring energy changed to gravitational energy, so we can substitute gravitational energy, and gravitational energy is equal to mgh. So Ug is equal to mgh is how you calculate the value of the gravitational energy. So we have our equations for kinetic energy and gravitational energy. So to wrap up this lab, remember that the y-intercepts were both 0. 0 meaning if you don't have mass, you don't have an object to accelerate for either of the situations. Now the slope value, this is the slope value of the velocity squared versus 1 over mass graph, which was twice the stored spring energy. And this is the slope value for the height versus weight, inverse weight graph. So the slope was the stored spring energy. So I hope that this was helpful. If you liked it, please click the like button down below. And I hope you all have a great day and an even better tomorrow. If you found this video helpful, don't forget to click the like button down below and subscribe to my channel, Cavi Coaches, and follow me on Instagram and Twitter @CaviCoaches.